Steve, I went ahead and put the record on, so you have it.
Okay. Okay, Sean, you should be able to be the presenter now. Hello, Sean Donegan. Apologize for the email, getting the email incorrect. You should be able to share your screen now and take over as a presenter. Okay, everyone, apologize for the slight delay here. Sean Donegan with Satelytics will be conducting the webinar today. Sean, without further ado.
Can you hear me?
Yes.
Great, super. Okay, well, good morning, everybody. My name is Sean Donegan. I work for a company called Satelytics. We're based in Toledo, Ohio, where today winter has begun in earnest. I think just east of us, there's down in Cleveland that fell this morning. So welcome to Winter Wonderland. This session will be focused on PFAS, and I think the gist of it was sort of doing more with less, which is sort of the credentials of our organization. We're a software company based in Ohio with customers across the globe. And for those of you not familiar, I'll give you the 50,000-foot view of how it works. Please feel free to interrupt and ask any questions. Two elements to this. I will not bore you to death with PowerPoint because I'm going to show you some of the software live also, but I think you'll get the gist of what it is that we do. So let's run through this. I'll make the materials available too if anybody wishes. So Satelytics is a software company at the 50,000-foot view. Most of the data we inhale in the 90% arena is from satellites. But of course, we're actually agnostic to the data source because going forward in life, things change rapidly. About 3 months ago, we received our first data from a stratospheric balloon, which operates in the 50 to 75,000 feet above the Earth's surface. And there we were taking in data that had a pixel resolution of between 5 and 10 centimeters per pixel on the ground. It doesn't have the same limitations as space, and therefore provides an even more granular capability as we go forward. So there's method in our madness about being agnostic to the data source. But the data could come from satellite, nanosatellites, aircraft, drones, planes, fixed cameras. We don't really care. What we're looking for is quality of the data in a particular format. We use the infrared spectra. How Satelytics works in this whole geospatial analytics world is the sun shines a light on the Earth's surface or a body of water, and what reflects back to a sensor that's typically on board a satellite, but of course, as I've already illustrated, could be any one of these other platforms, is a spectral signature. That spectral signature, a little bit like the human DNA, if we spit in a cup together or separately, we would be able to distinguish individual A from individual B. So our targets work in the same method. Methane has a different spectral signature than PFAS, which has a different spectral signature than oak tree or an elm tree or liquid hydrocarbons. And our goal as a company has been to develop algorithms and have a bucket full of algorithms, currently 30 plus. And the objective is that you could run those algorithms at the same time. Most of the companies we deal with, and our markets are power, pipeline, water, wastewater, and oil and gas, and we're adding mining, specialty chemicals, and rail this year, or we have added it, and we continue to add it, is that inside of any organization, there are different aspects for data. There could be several different business problems that could be solved using the same set of data. The whole initiative of doing more with less. So rather than individual groups making their own spend decision, if they all put their head above the precipice, they could share this data set, yet not compromise on the outcome, i.e. that we could run 30 algorithms all at the same time for different particular business needs. So if your need was looking at arsenic in water as opposed to PFAS concentrations from the use of AFFF firefighting suppressant, then from the same set of data, both of those outcomes can be derived and presented. So, and that's a fundamental reason why we don't charge user license fees. We absolutely want hundreds of thousands of people to use it. We don't expect you to be living inside Satelytics every day, but we're going to give you a very pointed area as to where you can direct resources, again, extending the whole reach of being able to do more with less. So our goal is pretty simple. It's to minimize really three major areas. Number one, loss of product. I mean, in oil and gas, if you've got a leak, you're losing revenue. So we want to minimize those consequences by giving as early a detection as possible. Number two, minimize cleanup costs. So in the example of PFAS, we know that it exists. We need to understand where it exists, location and quantification, and therefore minimize the cleanup costs by constantly monitoring that your efforts are actually hitting the target, number one, and two, being effective. And number three, while regulatory bodies and fines are not enjoyable by any stretch, they're certainly not the most outside influence. What we're finding more and more, take greenhouse gas reduction as a very good example. We're finding that outside bodies, the court of public opinion, has made life very, very difficult and will continue to make life difficult for many of our customers who are blue chip names around the world. And I want to caveat all of that by saying I've yet to meet an oil and gas executive that doesn't want to do the right thing anywhere. Everybody is very conscious of the footprint they have, their operations, and safety first is very paramount to both their employees and other people sharing the same space on the planet. So it's very important that we minimize that third consequence. So that's about how it works. It's pretty straightforward though from a gathering of data perspective. Let's go back to our light reference where we shine a light on the Earth's surface. We're using the near infrared, shortwave infrared bands. One day we hope to be using the midwave infrared bands because that will let us achieve certain objectives like gas speciation. Today we can detect and quantify methane. And what really sets us aside is not just the recognition of those spectral signatures of the target, but it's also identification on land and water. And in many instances, allowing us to see structure, salinity on land and water, and liquid hydrocarbons, and measuring them, whether that's in parts per million, parts per billion, or parts per trillion, as our early indications are with PFAS. So how it gets set up is pretty straightforward. You tell us how frequently you want to look at an area. Of course, that can vary tremendously. It can vary by seasons, so you could have temporal comparisons. It could vary by circumstance. An area may become heavily populated and therefore designated more high consequence, a risk factor, if you will. And thirdly, it could be based on just the overall areas that you are required to monitor and the frequency of how often you might want to monitor those. So once that data and those frequencies are set, in fact, I should suggest also that let's just say in today's event, our power companies will be asking us to accelerate data capture because with heavy snow could come down lines, down poles. So therefore, you might want a snapshot very quickly of what's changed to affect resources. So once that's set up, the data is captured, it's deposited to the AWS cloud. We run exclusively on the AWS cloud. There's nothing to install on the three form factors that we offer you. So smartphone, tablet, browser, nothing to install by design, so there can be no threat to the corporate network, and we never delete any data. So Satelytics as a company, you can come time and always have access to every bit of data that you've used. At the heart of what we use is what's called a convolutional neural network, and therefore we're developing synthetic data sets. To date, we have processed over 600 trillion pixels. Now, satellites vary in terms of their resolution, as you probably are all aware, from a very granular 30 centimeters by 30 centimeters per pixel square, so 1 foot by 1 foot, to a coarse set of imagery that would be very useful if you were examining a body of water like Lake Erie, and we were looking for toxic algae blooms and its derivative phycocyanin, chlorophyll, and phosphorus. Coincidentally, our first 3 algorithms that we developed, where we monitor and measure those things in parts per billion. But of course, we don't believe we're the only software program that you will be using. I mean, that would be very arrogant and very silly, misguided of us. So we have a full suite of API and web services that let you extract any of the imagery, any of the analytics, any of the alerts and alarms conditions to feed or accept data, both incoming and outgoing. So our first foray was looking at toxic algae blooms. And in that instance, what we were looking at was phosphorus, phycocyanin, chlorophyll A. We look at both of these on water and land. And of course, what you're seeing here on the screen is an image of a body of water where it's been processed, and you can see the color codes that represent the legend. Well, once we drop into the software in a few minutes here, you will actually see not just the color legend, but actually be able to click on any of the pixels and literally get the value that's within that pixel of that particular measurement, in this case phosphorus. Now you've got 2 options really as just a management technique. You can wait if you want until you've got the body of water that's laden with this level of phosphorus, or you might have said, what were the sources? So remember about the whole minimize consequence ahead of it. Well, what we're able to do is not just look at the water and the body of water itself, but also the land. And what you can see here is that the pooling of this phosphorus, as many people would point to immediately, it has to be agriculture. That's one of the first things that comes to mind. But in this particular instance, in this particular case, the phosphorus overload was caused by failed septic systems. So getting to the source and treating the source could be a technique. Early detection, eliminate the consequences of what comes forward. And that just doesn't have to be for chemical or constituent elements. It could be things like temperature, where in this particular case, surface water temperature and sediment had built up. So discharge from the, in this case, power station was being trapped by the sediment, as you can see here, the sediment bank, back into the intake. Therefore, the measurements of the surface water temperature were out of compliance. And of course, that then stretched us into nutrient loading, whether it was in rivers and streams and tributaries, whether we were looking for arsenic, turbidity, sediment. And our first foray into oil and gas, which was on the north slope of Alaska, where we monitored some 55,000 of bodies of water, where we were looking for arsenic, barium, copper, iron, and manganese. Not only identifying them, as you can see here illustrated with arsenic, but also measuring them in parts per billion. Our latest foray into that world has been into looking at PFAS. About 5 years ago now, I was doing a presentation in Washington, D.C. with a partner, Hunton & Williams, the law firm that is renowned for working with oil and gas and environmental. And we were doing a presentation. I saw a very interesting and inspiring presentation by a woman from the DOD, been with the DOD many years. And I took some quick shots and jumped out into the corridor and asked our chief scientist if he could take a look in his less than spare time I provide for him. And we started doing some early work on PFAS. And it was in conjunction with looking at the foundation of the firefighting foam that was used, AFFF, a fire suppressant, for many of you already know that, used in many preventative and also real life situations. So you would have, in their case, many military bases that had a firing range, drills, exercises, whatever other words they use for it, and had extensively used this firefighting foam. And to her best judgment, there were over 80,000 sites where the quantity and the location were not known, two of the things that we pride ourselves on. So we took it one stage further, and I said to Alan, can we get to Alan Adams, our chief scientist, can we get to work on some of the very basics of this? Fast forward 3 years, we got a call from one of our largest customers, BP, that said, what do you chaps know about PFAS, or words to that effect? And we pulled out our working papers, and they were extraordinarily impressed with our ability to see that signature, particularly AFFF. And then we started to do some laboratory work to ensure the substance on not only water, but also on multiple surfaces, which of course is in play. Then the process, typically 3 to 4 months, is that we would go through developing the algorithm. Then we would, over the locations, we would fly a satellite or task a satellite. That gives us complete control over location of where the satellite is captured. And then we physically pull samples. Those samples, whether it's soil or water, critical when it's water that the overpass of the satellite is coincidence with pulling the sample. The sample is shot with a backpack spectrometer. So we've therefore got satellite data, the backpack spectrometer as if we were grabbing the sample physically in the field. The physical sample's been handled in such a way that it's then sent off to an independent laboratory where the PFAS in this particular case is measured. Then when we get back those results, we then start to calibrate the nucleus of an algorithm, which is where we are today. And then what we look for is working alongside customers with known data sets, PFAS locations, to then grab physical or have data samples, not just physical, but either the data or the samples or both. And what we're looking for to build robust algorithms that are very accurate in their quantification is from the very low to the very high ranges of those measurements, in this case parts per trillion. What we're looking for are sample sets in each of those buckets. So let's say that we predetermine there are 20 categories of low ranges to high ranges. We're looking for sample sets in each of those ranges. That is how we start to work on the configuration of and measurement capabilities, quantification of any algorithm. And that really bears throughout all of our the way that we develop and have our algorithms for many years. And then as we pour in more and more data and develop synthetic data sets with this artificial intelligence, so we then report back to each algorithm that, for example, phosphorus, we measure accuracies to plus or minus 6 parts per billion. So we know that for sure. And that as we inhale more and more data, the incremental accuracy gets smaller, but you continue to make definitions. Our algorithm for methane, which took us 18 months to develop, and why? Because part of that ground truthing is challenging. We can't just simply release methane. We don't have that capability. So working alongside customers with known issues or areas of issues under non-disclosure or controlled releases at places like Meatech, Zico, Vivair, places that we've done controlled releases of methane alongside our customer BP, has allowed us to get to flow and flux rates of measurement of, in this case, methane. So let's take a look at how some of this works in real life, and then I'll stop and you can ask as many questions as you wish. So I want to go back. What you're looking at now on the screen is the Satelytics software, and basically you log on with a 2-factor authentication to the Amazon cloud. You can see it's a fairly busy demonstration site. I've got lots of different examples that I can reach from depending on the questions that come. But literally, you've got a pull right menu you've got a menu that pulls to the right where you've got various options: hot tapping, change detection, leak detection. You can keep that closed up if you wish. As I said, two-factor authentication. You also have a profile as an individual, whether you want text or email alerts. So fairly significant in its capability to offer you. And let's start with one that you've already seen. So let's just start with the one where I showed you the water quality and showed you where we started life looking at various areas on water. So you've just seen that example live on the PowerPoint screen. And what you're looking at here is a body of water. You can see the measurement to the right and the legend. You can simply close that down. We've got a very neat little feature called dual maps. And the default is that they synchronize. You can unsynchronize them. Very straightforward if you wish. And we may be looking at arsenic, and we may want to look at it at a different date. Remember, I told you we never delete any data. So right-hand screen, different date, same constituent. Or we could have said, well, I want to keep the same date, but I want to look at a different constituent. In this case, copper. Copper on the right, arsenic on the left. Some clever data capabilities. I can pick any area, and it will go back in time, all the way back in this case to 99, and the blue shaded area gives you the range of values, the red gives you the median. Or, as I told you before, you can pick out any of the point values. So any of the pixels, which could be represented by 30 meters by 30 meters on the ground, or 30 centimeters by 30 centimeters on the ground. And you can literally have any of that data. Any of the data, any of the elements can be pushed out into other software applications, or you could simply say, I just want to push out all that data into Excel. So I've got the constituent, the value, the longitude and latitude. Very simple, very straightforward, easy to do. The one element that I talked about being PFAS was where I said that we're in the final stages of ground truthing this. And if I just pick on a particular project area so you can see it on the screen, and I'll stick with the world imagery, turn off that so you can see that for a second. And I'm just going to zoom in so you can see this is the same type of process that you've just seen with the arsenic and barium, iron, manganese, and copper, and with one exception. In this case, we're measuring it in parts per trillion. So this is specific because we've had some questions around this before with peers and colleagues. This is looking at the compounds for PFAS that are found in the firefighting foam AFFF. There are other compounds. It's found in several other, well, many other products, as you may know, from non-stick pans and the Teflon that was used to line them, to various other agricultural products that we use. So the interesting twist here is that we have focused in on the area that's relevant to the industries that we service, namely power, pipeline, oil and gas, and that's AFFF firefighting foam. And again, the same capability, you'll be able to pick out the parts per trillion and then feed out that data into other areas. Now, whether it's arsenic, barium, iron, manganese, or PFAS, you'll be able to run those algorithms simultaneously. So we could have also been looking for at the same time. The one area that I showed you in the beginning was looking at chemical analysis on some of the waterways. And again, if I just pick on any particular area and I pick on a phosphorus load, what you're now going to see on the left-hand side of this particular case is phosphorus in that particular area. Or if I turn on the dual maps, and again, I can unsynchronize them if I want, I could be looking at a different area for the same constituent, and either side pick out any of the point values that I want. Very, very simple, and extract that data in other form or fashions that I wish to see. I'm going to show you two other areas, if I may. One is I'm going to show you the area for methane and where we are with that. And then I'll stop and take some questions and jump around if you want to see other examples. There are many other examples to show you, but methane was the most complicated area that we took a look at in the early days. It took us 18 months to develop. I'm going to pick on a particular area. And what you'll see here is not only the ability to determine methane as an airborne constituent and measure it in parts per million. So you see me clicking on the any of those pixels. The one exception with methane is that the federal government sadly restricts, or if it's the federal government, it's the body that controls outer space that controls the resolution. And methane shows up in what's called the shortwave infrared, so-called SWIR. There is one company, Maxar, formerly known as Digital Globe, that has a satellite that captures that particular infrared set of bands. And rather than it being at 30 centimeter, it's restricted to be sold at 3.7 by 3.7 meters, still significantly ahead of any of these NGOs that are out there touting that they're coming after you. But one of the things that we have developed is not just the parts per million, but also the flow rates. And the flow rates are accurate to plus or minus 6%. So, and we've done a lot of blind tests and blind studies around the world, different backgrounds, different environments that allow us to get to this particular environment. And then just to illustrate, I guess, one other tiny area, and because I mentioned it before, this is a good example of where some of these technologies are going in terms of resolution. And I make no bones for showing you this one, because this is the first set of data coming from a stratospheric balloon. What's significant about this, even if this is not your industry, is you can see the pole that's here. And sorry,
I'm not sure that we're seeing the same thing on your screen. You may have to refresh your screen.
Oh, excuse me. Sorry. Let me. Is that showing up now?
Hey, maybe reshare your screen real quick.
Okay. Better? Yes, no?
No, let's see, let's have you reshare your screen one more time.
Well, I stopped it, and I'm resharing my screen. Better?
Yes. Perfect.
Okay. So, did you see any of that software presentation, or?
I think our screen was frozen. Maybe go back just a couple of more slides.
Okay. Well, we're not showing slides. We're showing software live.
Okay, yeah. Show the live software again.
Okay. Okay. All right. Okay. So let me show you some of that very quickly again. So I started with showing everybody the high concentrations of arsenic, barium, iron, manganese. And I picked on a particular project area. And what I said was, here was arsenic in one particular screen. If I turn on dual maps, a little feature that we have, I can look at different dates and compare them side by side. The default is synchronized, but I can very easily unsynchronize those particular screens. I can pick on, I could pick on the same date, and I could literally pick on a different constituent. So in this case, copper. We never delete any data. You can see there's the legend as to the actual measurement. I can look at a particular area and pick on a set of data, and it will go back in time all the way back to 99. And the blue shaded area gives me the range of values. The red line gives me the average. I can pick out any of the point values I wish at the pixel level, which could be from 30 meters to 30 meters or 30 centimeters to 30 centimeters. Very, very simple. Any of this data can be downloaded. I can simply just spit it all out into Excel, which I had on the screen for you before. That data could also have been from looking at water. So in this case, I'm going to look at an area analysis of one of these water constituents that I picked on and illustrate for you phosphorus in a body of water, very straightforward. Or I could have turned on the dual maps and unsynchronize them and pick on a different area and look at that same particular constituent. Now the windows are working independently of one another, looking at two different areas. And I can pick out the point values measured in parts per billion for phosphorus on any particular area. Then I jumped from there to show you methane, and I'll just go back to the start of that so you can see. Here, methane, we've tried across the world, many different blind studies. I can pick on a particular area on a particular date. What I was explaining was that there's a restriction with the governments that, or the governing body that monitors space, of which the United States has a big say, and that SWIR, shortwave infrared, is resampled, even though it's captured at meters by 30 centimeters. It's resampled out at 3.7 by 3.7. I can pick out any of the point values. These are measured in parts per million. We see to a low of 10 parts per million. Cow poop is about 2.8, 2.9. But one of the huge revelations, and set Satelytics aside, is we can also measure the flow rates. They're accurate to plus or minus 6%. And for algorithms like phosphorus, we know that those are accurate to plus or minus 6 parts per billion. The one final thing that I was going to show you.
Hey, Sean,
yes.
You mind if I ask a question here?
Yeah,
so
please.
If you go back to that screen right there showing the methane,
yes,
if you can go back in time. What intervals can you go back in time? Is this a satellite image that's, or a hyperspectral image from a satellite where you get, say, 15 minutes a day from each of these, or is it, are there multiple satellites where it's a 24-hour day reading, or is it what's the time frame of the readings?
Yeah, so there's a whole bunch of questions you've put together there. So let me explain.
Yeah.
No. I just want to make sure I do them justice. There's nothing to apologize for. So what you're seeing on the screen here is a tasked satellite. There are two ways to grab satellite data. One, you can look back in time. And for high resolution data, it exists to the early 90s. But it depends on the area as to how full of an area is covered. For the less refined imagery, the coarser imagery, whether they are from government satellites like Sentinel and Landsat, then those resolutions vary from a low of 10 meters by 10 meters for each pixel to 30 meters by 30 meters. It goes back to 1980. They circumvent the Earth, and they are capturing pictures on a periodic cycle, typically every 16 days for the Landsat and less for the Sentinel. So you may have multiple data sets. They are captured roughly at the same time around the globe every time that they make an orbit. So it's not area coverage over one particular area, which we'll address in a second. But what you here is 3.7 by 3.7 meter spatial resolution tasked to a customer order. There is only one current satellite that has the shortwave infrared. I think that will rapidly change, but that's, I hope, addresses your question.
So the specific, and first of all, this is a great presentation. Thank you very much. And I believe hyperspectral imaging will totally change the world. The question is, so a bleeder valve or a mechanical vent valve, a mechanical vent valve on a tank. So if that tank is filling, then it would have emissions, and those emissions would be permitted. However, if it were having emissions every time it was viewed for a month, then it's probably not being filled on each of those instances. Instead, the mechanical breather vent valve has jammed, and so now the tank is venting all the time. And so, you know, in order for a company to see that, you know, they would have to, you know, there would be safety issues with getting up on top of the tank, etc. So it seems to me one of the values of your data would be that, you know, operationally people could, you know, see that, hey, this particular tank is always venting. You know, every time you look at this tank over a 2-month period or 3-month period, it's venting, which it wouldn't be. It's unlikely that the tank is being filled at all of those times. And so the same with bleeders. If a bleeder were jammed and venting all the time, has anyone asked for that form of the data to see if a particular, and I guess how, if they gave the UTM coordinates of all of their tanks, a company gave you the UTM coordinates of every tank, and then you went and looked and just produced a report that says, hey, this tank has been venting for, you know, 30 days or 45 days, whatever. So it is most likely experiencing a mechanical failure.
Right.
Has anyone asked for that kind of data or reports? What are the specific sort of operational functionality that people are asking for with regard to methane?
Yeah, well, first of all, great question. And I want to say yes on all fronts. So methane, as you probably know, BP is a significant customer of Satelytics. And you may or may not know, but BP became a shareholder in Satelytics in May of this year. The reason around that, or a lot of the reason, is the work that we've done around you know, greenhouse gas reduction and its drive to net zero. Interestingly enough, what you're seeing on the screen now is a set of data captured over the iPipe consortium in North Dakota. And this year we flew not only hyperspectral on a fixed-wing aircraft, what you're seeing is a drone capture over the area, and we captured satellite. So what we wanted to show and illustrate to everybody is there's no one size fits all. You will use, probably, in my professional opinion, you'll use satellites as the heavy lift, and then you will intrinsically set alerts and alarm thresholds to what you've just talked about. How often has this been going? What's the value of the data, the methane that's escaping? And it will be that sort of coincidence of parameters that will say to you, I need to deploy resources here because I think this is jammed or this is malfunctioning. And you may even say, well, I want to fly a drone over the area. Now, what's interesting is satellite data can take enormous captures of data. And all this nonsense that you hear about these NGOs, third-party people, that, you know, I'm not going to mention the names, but you probably can read them in the press. What they're basically telling you is, here's the state of Florida. Somewhere there's a theme park that has a mouse in it. Find it. You know, they've got no specificity. What you're looking at here is very specific data. So we can get within 3.7 by 3.7 meters with the satellite. Then you could potentially deploy, like you see here, a drone. This is at 8 centimeter spatial resolution using a FLIR camera on board of this drone. So it's measuring in parts per million. So it's not going to be one size fits all. It's going to be using smart techniques that get to the source of the problem. The short answer to your question is, everything that's being discussed about methane goes from storage to transportation to production. and the flaring, the events around it, flow and flux rates, all of that's up in the air. And I think, whether justified or not, I think there's a community that's nervous about, are they going to have the public finger pointed at them by these groups that say, we've got spatial resolution that's 400 meters by 100 meters. That's about as useful as a toothache, but they can make a lot of noise in the court of public opinion and therefore drive, a necessity for people in the oil and gas and pipeline community to have to act. Well, one further point to what I've said is that what's very interesting is that it's not just satellites, although I think satellites in the future will probably be the big answer if you were to ask, certainly doing the heavy lift. This is a stratospheric balloon. This is very, very interesting. At the 50 to 75,000 feet above the Earth's surface, it's a little lawless, meaning there aren't the same handcuffs and controls. This is, Airbus is in this. This happens to be a worldview data set. What I was illustrating was our community in the power industry. We can see the poles and we can see the cross members. What we can't see are the power lines until the resolution gets to 8 centimeters by 8 centimeters or better. And that now brings into play vegetation height to the line sag coefficient. I don't want to get into that, but it's an area that's very interesting to us because we already work in the power industry. And it will prevent these wildfires if you could do great vegetation management underneath those line sag coefficients. What's fabulous about this is the balloons, and they follow the term, I think, is racetracks, and they use helium for lift, and then they use another engine for ballast where they're using the thermals to move east and west. The great thing about this from a pipeline oil and gas perspective is it can follow a pipeline. Traditional satellites orbit north-south, so that's a huge positive. The second is they can stay up there for a long period, and because they move at a relatively low speed, one of the questions you asked was, can I get multiple captures or monitor an area on a greater frequency during the day? That potentially could happen here. And the third thing, which is really relevant, is say the telemetry improves in 1, 2, 3 years. I mean, look at the way cell phone technology has dramatically changed. Better cameras, faster chips, etc. The balloons could be brought back down to Earth, new telemetry fixed and put back up. You can't do that with a satellite. So it goes back to my point that there'll be multiple data platforms, and those that can show how you fuse that data, many of the elements I've shown you is that capability to fuse that data, are in play. And then just to sort of round off, we also developed something called Satelytics for the non-connected world. So this is simulating your cell phone. This happens to be over North Dakota, this iPipe consortium. And now I can be looking at any of that data without having to have a cell or an internet coverage in the field. And I can record and take photographs. And then when I get back to the office, it will synchronize it all back up in one neat record. And that sort of is a quick snapshot of some of the touch points of Satelytics. It also applies to landslips, encroachments, change detection, water crossings. We have quite a plethora of offerings, and we want to continue that. Build the bucket of algorithms, allow the customer to spend, let's say, $10,000 and share it amongst 10 or 15 different departments, therefore driving huge efficiencies, and most importantly, getting out ahead of events to minimize consequence, minimize loss of revenue, and ensure that the court of public opinion is firmly closed. And I'd be delighted to take any questions that may come.
Are there any questions from the audience? And you can raise your hand over here by clicking this, or show the chat. Okay, Sean, I definitely have a couple of other questions. One is, for due diligence.
Yes.
We did a lot of due diligence over the years. So for PFAS, if an entity were looking to buy another entity, could they go get the UTM coordinates for all of the areas that they were going to buy, and then go back and look at the history of PFAS concentrations at those entities, at those UTM coordinates?
Yeah, great question. And thanks for the really great question. Actually, we've done that for years in the wastewater industry. We actually started life in the wastewater industry. We live on the edge of Lake Erie, that's known for its algae blooms. So some of our water clients, what they've asked us to do is to do what they call a brownfield site assessment. So they want us to look at a whole swath of land and tell them what constituents are there and present and in what concentrations. So that's a very similar capability. Depending on where it is in the world, before they would spend any money, we could tell them what data exists in all the archives of all the satellite companies and which is usable on what dates. So if they have, let's say they have some known incidents or other challenges that they have known dates over, we could surround the purchase of any archive data and assessment around specific dates.
Okay, and the use on the methane side, where you mentioned the satellites. Which satellites? I guess which what is the data source for the methane? And if someone acquired data from satellites or other methane data from drones, from drone surveys, I guess first question would be, which satellites is the data coming from for methane?
So methane, the data is coming from the Maxar constellation, digital globe, and it's using the shortwave infrared, SWIR. And that was actually started by Airbus back in the 70s, and they stopped putting it on their subsequent satellites. I think they're revisiting that as we show that there's a huge interest in that. So today it's Digital Globe, formerly known as Digital Globe Maxar, with their Worldview 3. The methane bands also exist, but at coarser resolution in some of the government-owned satellites, Sentinel and Landsat. There are some other bit players that have put up some methane-only sensors. But of course, the question I would have is, I'm not sure that our customer base is going to buy one set of data for methane and then buy other sets of data for other, what they're looking to do is drive efficiency. So from a set of data using the geospatial analytics of Satelytics, you can not only look for methane, but some of the other problems I've also spoke to. For the drone work, for when we flew on fixed wing aircraft, we used a company called Spectier for hyperspectral on a fixed wing aircraft. And then we also used Compass as the drone company to fly cameras over the localized area. It took them 6 hours to cover 100 acres, which of course in satellite terms, that's not a lot. But again, we're showing fusion of data from different sources. That was the objective.
Okay. Hey, Eric T. Meyer or Mark, Tom Gorman, any of y'all have questions?
Steve, I can make any of the materials available at any point if your audience would prefer. So just let me know what else I can do to help.
Okay, thank you very much, Sean. We will.
You're
make,
welcome. Thank you. Thanks, everybody.
Available.
Stay healthy.
Okay, thank you all very much. Take
Bye-bye.
care. Bye-bye.